So, we had done relativistic kinematics, Lorentz transformation going from one frame to the other frame, and then length contraction, time dilation, synchronization of clocks, velocity addition, all these things we had done. And today the agenda is to solve some problems, so that these equations that we have derived are practiced well. So, our first problem is the following. A particular particle created in a nuclear reactor leaves a 1 centimeter track before decaying. So, in nuclear reactor you have varieties of nuclear reactions taking place, new particles are created and then those particles move, and then in the detector system, there is some kind of detector system. When the particle moves through the medium, it leaves a track, and when that particle decays, then the track is terminated. So, particular particle created in a nuclear reactor leaves us 1 centimeter track before decaying. Assuming that the particle moved at 0.995 c, calculate the life of the particle, one in the lab frame and then second in the frame of the particle. So, when the particle is created, the track starts because the particle is moving, and when the particle decays, that particular track is terminated. Maybe some other particles will be created and this more tracks will be created, but that particular track is terminated. So, the length of the track is 1 centimeter, the speed is 0.995 c. So, you can calculate what is the life from particle created to particle decayed. So, in the lab frame things are just simple, no relativity needed. In just if I am in one frame only, then things are just your class 9, 10th, 8th arithmetic and physics. So, the life, that means time is distance travelled and divided by the speed, and that is 1 centimeter and divided by speed is 0.995 c, 3 into 10 to the power 10 centimeter per second. Okay, so, you can cancel this centimeter and this whole thing will become in seconds. So, it is 1 divided by 3 into this is 15, 1, then this 27, so 28, and then 2, then 27 and 2, 29. So, it is this, and into 10 power 10, these many seconds. You can work out how much it is for these many seconds. So, if you do it, the answer is 3.35 into 10 power minus 11 second. Okay. So, this is simple. In the lab frame it is moving and I am seeing that it takes some time and the length is 1 centimeter, it covers 1 centimeter and the speed is known. So, I can calculate how much time it has taken in covering that 1 centimeter. So, that is the life. Now, in the frame of the particle, what is the same time interval? Particle created, particle decayed, time interval. In the lab frame it is this, in the particle frame what is the time? So, you can see that the particle created and particle decayed, these two events are 1 centimeter apart in the lab frame. So, this is not the proper time interval, whereas if you go in the particle frame, if you put your origin on the particle itself, so the particle is created at the origin and the particle decays at the origin. So, the two events are occurring at the same position. So, that time interval will be proper time interval, and proper time interval is the smallest time interval. So, the proper time interval is smaller than this by what factor? That gamma factor. So, this is in the lab frame, and then in particle frame, that same time interval at life, particle created to particle decayed, that same time interval is proper time interval, and proper time interval is the smallest one, and therefore it will be this 3.35 into 10 power minus 11 second, and multiplied by square root 1 minus v by c, which is 0.995 square. So, these many seconds. So, you can work it out how much it is. I can use my calculator. How much it is? This is 3.35 into 10 power minus 11 second, and then multiplied by, that is 0.0998 and so on, 7, something like that. And if you multiply this by 3.35, it is 0.33. It is 0.334, like that, 5, 8, and that into 10 power minus 11 second, or you can write it as 3.35 if you want to round it off, into 10 to the power minus, you have multiplied, so you have to divide, minus 12 seconds. So, almost a factor of 10. If you see here and you see here, it is a factor of 10. So, 10 times is the is smaller. This proper time interval is 10 times smaller than this. Okay. So, let us go for the next question. So, here is the next question. A person standing on a platform finds that a train moving with velocity 0.6 c takes 1 second to pass by him. Find A, the length of the train as seen by the person, and B, the rest length of the train. So, you have a platform, and on that platform some person is standing, and then the train, there is some train, and that train is moving and moving with 0.6 c. These numbers 0.6 c and 0.8 c you find many times in the problems, because when you see 1 minus v square by c square square root, these are very handy. Okay. So, that square root 1 minus v square by c square will be 0.8, and if this is 0.8 c, then that will be 0.6, so very handy. So, find the length of the train as seen by the person, and the person finds that it takes 1 second to pass by him. The train takes 1 second to pass by him. That means the engine is here, and then the last coach is here, the rear end is here. So, the train has passed by him and it takes 1 second. So, you know how much is the length, how much is the engine moved in 1 second? It has moved at this speed. So, this is for that platform, this is for the person frame. So, the time taken is 1 second, and the speed is 0.6 c, and so the distance covered by the train or by the engine in 1 second, that will be equal to 0.6 c second. So, 3 into 10 power 8 meter per second, and multiplied by 1 second. So, it is 1.8 into 10 power 8 meters. So, to practice all these relativity equations, we create these hypothetical situations. The length of the train is 1.8 into 10 to the power 8 meters. So, these are all hypothetical situations, but to bring out that meaning of equations, we use these unrealistic numbers. So, at 1 second, that last rear part is here and the engine is at this distance. So, that is the length of the train. So, this is the length of the train. Okay. And when I say that a person finds that, okay, here find the length of the train as seen by the person. So, this as seen should not be taken as seen by the eyes. As seen means in that frame, in that person's frame, what is the length? How it finds that length, we are not concerned with this. In the person's frame, this is the length. So, that is the meaning. We will be using these kind of words, as seen by, as observed by, but do not think that the process of observation or process of seeing is involved in solving such problems. So, this is a person's frame, and then we need rest length. What is rest length? Rest length is the length in the train's frame itself. Okay. Rest length of a train means from the train frame you measure the length of the train, that is rest length, and this is moving length, because this is with respect to the platform, with respect to the person, and the train is moving. So, this is the moving length and this is the rest length from the train's frame, and rest length is always larger than the moving length, and therefore, this rest length will be this length. If I call it L, this will be L, and then divided by square root 1 minus v square by c square. It has to be larger, so you have to divide by this. So, this is 1.8 into 10 power 8 meter and divided by 0.8. Okay. When you put 0.6 here, the square will be 0.36 and 1 minus 0.36 will be 0.64 and square root will be this, and so it is, how much it is? 9 by 4. So, 2.25 into 10 to the power 8 meters. So, at this speed, because of length contraction, the length 2.225 into 10 power 8 meters of this train, the rest length is this, and because of the speed in the person's frame where the train is moving, it has reduced to this much. Okay. So, let us go to the next question. So, here is that question. It says that at time t, a particular clock A fixed on the x axis of the frame S agrees with a clock B fixed on the x prime axis of the frame S prime and opposite A. So, you have a frame S, let us say this is frame S, and in this frame at time t, a particular clock A. So, you have a clock A here and it shows time t. So, fixed on the x axis of the frame S agrees with a clock B fixed on the x prime axis. So, you also have a frame S prime, and since we are talking of time t, I am not making the two origins coincide. So, there is a clock fixed in S prime and this clock is B, it's just opposite this A, and it agrees, that means this clock also shows time t. So, that is the meaning of the first sentence, that at time t a particular clock A fixed on the x axis of the frame S agrees with a clock B fixed on the x prime axis of the frame S prime and opposite to A. So, these two agree with each other, and this time t is measured from S frame. Remember, this time t is measured from S frame, and at this time there is a clock here and that also reads t. So, this for this event this t prime is same as t. Find the x coordinate of these clocks as seen by S. So, you need x coordinate of these two clocks as seen from S. So, you need this, you need this. So, this x coordinate is, let us say, x. So, this is our event, this is our event. These two clocks are opposite each other, that is the event. A and B are opposite each other. This B is as seen from S, this B is moving. So, at a certain time this B is opposite A, that is the event. So, you have x and you have t. When you make the transformation for this same event as seen from S prime, what is the time? So, since the event is occurring here, the clock here will read that time, and that time is t, it should be t prime. So, this is in S, and therefore, in S prime for the same event t prime should be equal to t minus x v by c square and then square root 1 minus v square by c square in denominator, and this is equal to t. It agrees, these two clocks agree, and the question is, what is this x? How much is this x? So, you can work it out from here. It is t and 1 divided by square root 1 minus v square by c square and minus 1. So, what I have done? I have written this term and I have written this term. So, minus 1, and this should be equal to, so I have taken this thing here and I am taking this thing on that side. So, it is x v by c square and then square root 1 minus v square by c square. Okay. So, in this equation I am transposing, this t comes to the left and this minus x v by c square divided by this, that goes to the right side. And so, from here you can write what is x. If you multiply by this square root 1 minus v square by c square, it is t times 1 minus square root 1 minus v square by c square is equal to x v by c square, and hence x is equal to c square by v into t and then into 1 minus square root 1 minus v square by c square. So, that is the coordinate. At this coordinate the clock of S frame, and at the same position the clock B of S prime, they coincide, the readings coincide. Okay, they agree with each other. This is t, this is t. So, that is our first part. Now, the second part is, what does the clock C fixed in S prime opposite to the origin of S? So, clock C is opposite to the origin of S. Read, what does this clock C read at this instant t as observed in S? So, in S frame at time t these two clocks are agreeing. At the same time t there is some clock of S prime, all right, there is some clock of S prime which is opposite to the origin. This is the origin of S. So, there is some clock here C, this is the clock C, they are all moving, they are all moving. But at this instant t, this clock is opposite to the origin, and the question is, what does this clock read? How much is this clock read? So, this is the question. Okay. So, let me make some space. Now, this event, this event, this clock C is opposite to the origin. What are the x and t as seen from S, and from there we can get what is the reading of this clock. So, our event is C comes opposite to the origin O of S. This is the event. Now, in S frame, where did this event happen? It happened at x is equal to 0. At what time? T equal to t. At this instant t. So, the timing of this event is t, and the position of the location of this event is x equal to 0. So, what should be t prime? What should this clock read? According to S prime, when did this event occur? And that will be read by this clock, because this clock is here. So, in S prime frame, you will have t prime, which is t minus x v by c square, and then divided by 1 minus v square by c square, and x is 0. So, t prime is t divided by square root 1 minus v square by c square. So, that is it. So, this clock is reading t, and this clock is reading t divided by square root 1 minus v square by c square at the same instant. At the same instant t, this reads t and this reads this much. And the third part is show that the rear clock C leads the front clock B by L V by C square, where L is the rest separation between the clocks. So, you see this t prime is greater than t, this t prime is greater than t. So, this reading is more and this reading is less, this is t and this is more than t. So, the rear clock, since everything is moving towards right, this is the rear clock, this is the front clock. Rear clock leads. By how much does it lead? So, you can subtract, this reads t and this reads t divided by this much. So, you can find how much is the difference. So, let me write it here. This C leads B by how much? T divided by square root 1 minus v square by c square and minus t. And then you want to show that this rear clock C leads the front clock B by LV by C square, that we have studied, synchronization of clocks, where L is the rest length between the clocks. So, let us calculate this LV by C square. Let us calculate this L times V divided by C square. I think I can do it here. L, the rest separation. How much is the rest separation? What is the separation between C and B as seen from S? That separation is just this x, because at time t, at position x, this clock agrees with this. So, this B clock is at this coordinate and this C clock is at the origin. So, from S, the separation between B and C is x, and that is C square by V into T, and then 1 minus square root 1 minus V square by C square, that is the separation between B and C as seen from S, and in S both of them are moving with velocity V. So, the rest separation which is larger than the separation in any other frame, rest separation L will be equal to this quantity it's larger. So, remember you have to divide by square root 1 minus v square by c square. Okay. So, this is equal to c square t by v, and then 1 minus this is 1 divided by this, and yeah. So, 1 divided by square root 1 minus v square by c square, and then minus 1. So, it is minus 1. This is L. So, what is L v by c square? L times v divided by c square. This is your rest separation L. So, L v by c square is equal to v by c square. So, this cancels out and you are left with t, and then 1 divided by square root 1 minus v square by c square and minus 1, and that is same as this. That is same as this. Okay, so everything is consistent. This rear clock leads the front clock by LV by c square, where L is the rest separation. So, let me go to the last question of this lecture, and that will be on velocity addition. So, the question is, two rockets each of length L naught, it is rest length, remember when I say each of length, rest length L naught are approaching the earth from opposite directions at the same speed c by 2. Find the length of the one rocket in the frame of the other rocket. So, that is the question. So, you have two rockets and the rest length is L naught here and then here, and then they are approaching each other, and not each other, yeah, each other also, and there is earth somewhere. So, this is at speed c by 2 and this is c by 2. So, they are approaching the earth at the speed c by 2. So, in earth frame this is c by 2, in earth frame this is c by 2. The question is, what is the length of this rocket as seen or as measured or as observed in this frame? And remember, seen is not seeing with the eyes. Okay, so first we calculate the velocity or the speed of this rocket with respect to this one. So, if I call it B, if I call it A, then velocity of B in the frame of A or with respect to A. Okay. If it is Galilean transformation, it will be c by 2 plus c by 2 equal to c. But here it will be V will be equal to V1 plus V2 and then divided by 1 plus V1 V2 by c square, that is the equation. So, c by 2 plus c by 2 divided by 1 plus c by 2 into c by 2, so that is 1 by 4, and then c square by c square is 1. So, it is c, this is 5 by 4, so it is 4 by 5 c. So, speed of this rocket in the frame of this rocket will be 4 by 5 c according to Lorentz transformation. Now, you can work out what will be the length of this rocket as measured in this frame, because now this we are talking from this frame, and from this frame, from this rocket frame, the other rocket is moving at a speed 4 by 5 c, that is 0.8 c, it is moving like this, and therefore, the length should be contracted. Length of B, this is B, is equal to, as in from this A is its rest length, which is L naught, and then contracted by this factor 1 minus V square by C square, that is this 0.8 square, and that is 0.6 L naught. So, that is the length measured in this frame, length of this rocket measured in this frame. So, these are the kind of questions, these are the kind of numerical problems that we solve in relativity. Remember, you have to consciously, because it is not coming from our common sense. So, you have to consciously use the equations, frames, which frame, this frame, that frame, rest length, moving length, proper time interval, improper time interval. So, you have to be conscious.